This is going on page 50 when we are done. We are going to be talking about exponential functions. Not brand new, right? Melvin, what are you doing? Huh? Yeah, nothing. Wrong notes, but okay. Exponential functions, not brand new. You talk about them first in Algebra 1, then we have talked about them a little teeny tiny bit. But obviously we study several different types of functions, and they show up in every math class from Algebra 1 to Calculus. Like, these are the big three. And these three families of functions, they show up on the SAT and ACT also. I'm sure you noticed that when you took the PSAT or SAT, because I think that was one of the things when y'all gave me feedback that you might have liked to have known a little bit more about before you take the test. All right, and remember, to be an exponential, it's not just about having an exponent, because we have an exponent here. You have to have a variable in the exponent, right? That's what makes it an exponential function. Okay. Exponential functions. Some of the most important functions in the real world, because that's what we always wonder, right? Why do I even need to know any of this? Well, are you going to ever have to, like, graph an exponential function by hand or something? Probably not, okay? I mean, the only reason I do is because I teach it. Otherwise, I don't know that I'd be doing that in the real world, but having an understanding of that is very important. So that has to do with population growth. Money's a big thing. If you are looking at buying a car or a house and you're interested in interest or debt or whatever, there's all kinds of calculators out there on the internet that'll just do it for you. That's fine. Let it do the math. But you having an understanding of what's behind the math helps you understand the big picture a lot better than somebody's clueless and just numbers are popping up, okay? And then obviously radioactive decay, spread of disease, and again, on the SAT. So let's talk about some key characteristics, most of which we already know. So here's your general form of an exponential, okay? That's like your parent function, okay? Without any transformations or anything, although A is kind of a transformation, but B is greater than 0. So when we're talking about growth and decay, B is positive, and then it says A and B are constants with A can't be 0. If A was 0, the whole thing would be 0, right? And that wouldn't even make any sense. And then B can't be 1, because if B was 1, that exponent wouldn't be changing anything. Okay, that makes sense to you? All right, so A represents, and this is just like our geometric sequence, that first generic one that I said you don't necessarily have to remember, but that's the form that is in. So the A right here is the same as the G sub 0, which is just the initial amount. Because if I put in a 0 for the exponent, then the B term ends up just being 1. And then B represents the common what? Oh, not a difference, but the what? Ratio. Yes, thank you. All right, so exponential growth. A is greater than 0, B is greater than 1. If A was negative, then the A value still does the A thing, but the negative really does a reflection, right? As a transformation. Does that make sense? But right now, if we're talking about strictly exponential growth and decay, A is positive, okay? We will have reflections, but then we're not really talking about exponential growth anymore. It kind of changes that. And so this function here, is it increasing or decreasing? Increasing. As x gets bigger, the y values get bigger, right? So this function is increasing. Is it concave up or concave down? Concave up. Okay, good. So that concavity is a new thing to tie to this because we haven't talked about it until this year. Then we have exponential decay, which again means that we're just talking about that when A is greater than 0. If I have a reflection, then it's not really exponential decay anymore. And this time, B is between 0 and 1, which means it's a fractional amount, 1/2, 1/3, 0.7, whatever. And is this one increasing or decreasing? Decreasing. And is it concave up or concave down? Concave up. It's also concave up. Up like a cup, right? Concave up. So since exponential functions are what they are. Somebody knocking. Hello. Thank you. Thank you. You can grab a snack at the back there. Since they are what they are, this is increasing, and it doesn't ever change. Like if it's increasing, it's always increasing. If it's decreasing, it's always decreasing. And the concavity is always whatever the concavity is. Make sense? There's no change in any of that. So when we look at our fun chart, and you have some room down here, we hadn't written that in a minute, so let's write that down. If I don't have any change in concavity, then I don't have a point of inflection, because that's what happens there, right? Also, if I don't have any change in concavity, then my rate of change is either always increasing or always decreasing. It's not going to change between the two. If the function itself is always increasing or always decreasing, then think about what happens when you're increasing and then decreasing, or decreasing then increasing. That gives you relative max and mins, right? So we don't have that because we don't change from increasing to decreasing, which means also whatever my rate of change is, it's either positive and always positive or negative and always negative. Okay, that makes sense? So we haven't used the fun chart in a while. We got to make sure we know how to use it. All good so far? All right. Jenny, you okay? Okay, you look miserable. Whatever's going on. I'm just making sure. All right, so basically that's what this says. Exponential functions are always increasing or always decreasing, and they never switch, so they have no relative extrema. I have no relative maximums or minimums. For concavity, we're either always concave up or always concave down, so then we have no points of inflection. So for our exponential growth model, is the rate of change increasing or decreasing? Rate of change. Increasing. How do we know the rate of change is increasing? Because it's concave up, right? This is concave up. I look at my concavity. If I want to know about my rate of change, and if it's increasing or decreasing, I look at concavity. Since that is concave up, my rate of change is increasing. What's going on with the rate of change here? Decreasing. Okay, so then for the exponential growth, is my rate of change positive or negative? Is the function increasing or decreasing? Yeah, it's increasing. Since the function is increasing, the rate of change is positive. This function is decreasing, so the rate of change is negative, right? Remember how to use that? Make sure you're writing it down when you need it. All right, so then another new part of that. Do you have a question? Here. The rate of change. Okay, so if rate, yes. Because for the rate, so here, the rate of change, well, let's just write this down. So we'll put rate of change, oops. There you go. Rate of change. Because this was the function. So my rate of change, since my function is concave up, my rate of change is increasing. And since the function is decreasing, it's negative. Right? Does that make sense? Okay. So let's just go ahead and do that over here too. Rate of change. Okay. So since the function is concave up, my rate of change is what? Increasing. And since the function is increasing, the rate of change is what? Positive. Okay. So remember how to separate that. If you're talking about the function, you don't need the fun chart. If you're talking about the rate of change, you need the fun chart, and then you look at the function to figure out how to match it up. Okay? We'll get on that. Any other questions? Awesome. All right, in behavior. So in behavior, we're going to tie this to our limit statements. And it says if it's in general form, like we have, okay, there's no vertical, there's no translations or anything in there. As the input values increase or decrease without bound, if I'm increasing without bound, where am I heading to? infinity, okay? And if I'm decreasing without bound, I'm heading to negative infinity. Good. So as we're going to the infinities, the output values will increase or decrease without bound, or they will approach 0. And let's talk about why that is. When we go back up here and we look at this function, as x is increasing without bound, y is heading to where? Infinity. Okay, so as x is decreasing without bound, and we look at our actual function, like a times b to the x, let's just say that this is 2 to the x power, okay? Whatever, 2 to the x. Then this has to be 1. If that was 5 to the x, that would be 1. If it was 20 to the x, that would be 1, because anything to the 0 power would be 1, right? As we have negative x values, that's going to start taking the reciprocal, so I start getting smaller and smaller numbers. Is there a number I could substitute into the exponent and get 0 as my answer? No, right? It's not possible. Is it going to get super duper tiny? And we're going to get really close to 0, right? We get arbitrarily close. That's words that they like to use as well. So that means I have what here at y equals 0? An asymptote. Good. And remember from all of you poor little children that had Mrs. Archer last year, it's asymptote, right? Not asymptote. All right, so we got an asymptote there. And so this, when we're approaching 0, that is because we have a horizontal asymptote. So we have to recognize things about the function, be able to tie it to the fun chart so that we can recognize things about the rate of change. Is really with us? Okay. And then we also have to be able to do our limit statements. Okay? So any questions at this point? All right, let's flip this over and write our limit statements. All right, end behavior, left end behavior, limit as x approaches what? Negative infinity. And remember, 99% of y'all are doing beautifully with your limit notation. There's still some people where I can't really tell if it's just a handwriting issue or if you don't know how to do it correctly, so be careful. We stack this. Now this doesn't have a name. Let's call it f of x. And then f of x goes in front of it. Right. Another way to say this, instead of as x approaches negative infinity, as x decreases without bound, okay? And those mean the same thing. You could see it in words, you could see it as a limit statement, but you got to understand, where you're going with that. So as x is heading to negative infinity, where is y heading? 0, okay? So again, I can say this a few different ways. The limit as x approaches negative infinity of f of x equals 0. That's how I can read that. I can also say as x decreases without bound, y gets arbitrarily close to 0. Does that make sense to you? We good on that? Okay. So then my right limit as x approaches infinity. Well, that's what I was going to ask you what it would be. Yeah. Or as x increases without bound of f of x, what is this answer? Infinity. Very good. Everybody okay with that? All right, so I'm going to give you a minute. I want you to write your limit statements for B, and then we will check ourselves. Say that again. Oh, thank you. Yeah, it doesn't have a name. Well, let's call this one H, just to be different. So as x decreases without bound, what's my limit? Negative infinity. Very good. As x increases without bound, what's my limit? 0. Very good. Now, once we get to transformations and we translate up or down, let's say that this was like a +3 situation, then your asymptote goes with that. So instead of approaching 0, we'd be approaching 3 because it went up with it. Okay, we'll talk about that again when we get there. All right, so on C, I do not have, well, I have a name for this one, but I don't have a graph. But given what I have, is this exponential growth or decay? Decay. And what do we look at to figure that out? B. Yeah, so right here, B is between 0 and 1, right? So B is between 0 and 1, which that means that it is decay. And then I don't have to like plot points and stuff. I just know that the graph looks like this, and then that's all that matters, right? That because I just basically use that situation to do the rest. So then the limit as x approaches negative infinity of g of x, and remember, we don't call everything f, we call it what it is, so I don't have to call you all Melissa, right? And what is that as we approach negative infinity? Infinity, good. And then the limit as x approaches infinity of g of x is 0. Now, let's say that they gave me that same equation, but 5 was negative. If 5 is negative, that means I'm going to have a reflection. Would I be reflecting across the x-axis or the y-axis? The x-axis. With exponentials, it's really easy to tell what affects x and what affects y, because anything that affects x is going to be up in the exponent with x. So since that's not, that means I'm changing the sign on y, and when I change the sign on y, I reflect in the x-axis, right? That makes sense? And so if that happens, then if I reflect this in the x-axis, then it looks like this, right? So we'll all go okay with that because that's the one transformation that's actually going to show up today. Any questions on that? Yeah, exactly. And it doesn't become, oh yeah. So like here. So like if this one had a negative in the front of it, and then I'm reflecting it down, then it's going to look like that. Good question. What else we got? Anything else? And if you are, let's say it was a -5. What I think would be safe for most of us, I know not all of you want to do any extra steps, but at least if I'm explaining to you, what I'm going to show you is, if this was a -5, I'd say, okay, we're going to ignore the negative. We're going to do this so that we can get that, our mind wrapped around that. And then we'll draw a second one where it's reflected. That way you don't draw them the opposite way, which is easy to do. Good question. Anything else? All right. So this here should be a piece of cake. It says for each of the following, determine if the exponential function is increasing, decreasing, or concave up or concave down. So this one right here, concave up or down? Up, okay? Increasing or decreasing? Decreasing, right? Because we're looking at the y values are getting smaller. All right, but then let me ask you this then, same one. Is the rate of change increasing or decreasing? Increasing, why? Because it's concave up. Is the rate of change positive or negative? Negative, why? Because the function's decreasing. Okay, good. All right, so B, is it concave up or down? Down. Is the function increasing or decreasing? Decreasing. All right. So then here I don't have a graph, but I can draw one, right? Is this exponential growth or decay? Growth, because B is greater than 1. So this is growth. And then it's going to look something like that, right? That's good enough to get the rest. Concave up or down? Up. Increasing or decreasing? Increasing. Okay. Everybody okay with that? What questions you got? All right, so, and also remember this. When we were talking about exponential growth and decay, it says A is greater than 0. So this is my exponential decay. This is exponential growth. We don't really talk about it here because A is not positive, so there's a reflection. Like it still has applications, but it's not, we don't talk about it that way. We're okay with that because A is not greater than 0. All right, last thing. We have a table of values like we did yesterday. Yesterday when we had this, it was just asking us if they were linear or exponential. Today it says linear, quadratic, exponential, or none of these. So what do I start by looking at? The x, okay? And somebody earlier today said it beautifully. They said it's the change in x, and that is exactly what it is. The change in x. So 6 minus 1, that is 5, and 5, and 5, and 5, right? So I have equal length input value intervals, right? Which is something I want. Check. Then what we did yesterday, we just had to decide if we were going to look at differences or if we were going to look at ratios. And because I don't have to write them both out if I don't have to. If I put 5 over 3 and 9 over 5, are those the same? No, so I don't think I'm going to go with ratios. Instead, I'm going to look at the differences. And remember, it's the second minus the first, so the difference here is 2. 9 minus 5 is 4, then 8, and then 16. So is this linear? No, because my first differences are not constant, but what we just found, this is the change in y. And my slope is the change in y of the change in x. So I'd have 2/5 and then 4/5, 8/5. Those aren't the same, right? If I had done my ratios there, that would not be the change in y. So it's not like that's always the change in y. So now that I have that, even without doing it, you can look. Would your second differences be constant? Yes? No? 4 minus 2 is 2. 8 minus 4 is 4. So those two aren't the same. I don't have to think about anything else. So it's also not quadratic. But now, what does it, looking at my orange numbers there, what does it look like it is? It's doubling, right? And since I'm multiplying by the same thing over and over again, that would make it exponential. So let's check that. Let's look at the ratios. So here, I'm going to be multiplying by what? 2, because I put 4 over 2. Here, I multiply by 2. Here, I multiply by 2. Yesterday, the first thing we did, either our ratio worked or our differences worked. That's because that was an exponential with 0 transformations. Here, this has a translation in it. Basically, you double it, and then you add whatever. Like, there's something going on there, right? So there's other transformations within there. So now we have to start looking at more than one thing. So clearly the first ratios didn't work, so we do our differences, and then you see if you have ratios there. That is what makes it exponential. Okay? Everybody okay with that? Any questions? And we'll use that information to build functions afterwards. All right, any questions at all? Okie dokie.